Okay, hello. Today's lecture will be about expansiveness for flows on non-compact spaces. Okay, this will be the introduction of my joint paper with Iam C.A. Okay, I will start with the following situation. Expansiveness for flows are defined by Bowen voltage in the following way. A flow phi is of a metric space. X is expansive if for every epsilon positive there is a delta positive such that if 2 points x and y in the space satisfies distance between ft of x, f alpha t of y less than delta for every t in R, and some alpha from R to R continuous fixing 0, then the y belongs to the piece of orbit between minus epsilon of x. This is the classical definition of Bowen and voltage. Those authors proved many properties in compact metric space which are not going to relate here. I mean, no, I will not tell you what properties are, but you can find those properties in the Bowen voltage paper. What I want to report here is the following. Expansivity is not invariant by topological conjugation. Okay, what does it mean this? We say that flow phi in space X and flow var phi in space Y are topologically conjugated if and only if there is a homeomorphism from Y to X, homeomorphism, such that H of carry the flow of carry the flow of var phi to the I'm changing the phi t composite with H is equal H composite with phi t. Okay, this means that the H carry the flow of, let's see, this is var phi, the var phi flow into the phi flow. Okay, here. Okay, this is the meaning of topological conjugation. There is a stronger property which is topological equivalence, which I will not talk here. Now, what the problem? That expansivity is not invariant by this property, by this relation. And there are many examples for that. The example is this. You pick a flow, pick this flow equal a power t omega in the space X, defined by as the element of R3 such that theta equals 0 and xy different from 0. What is this? This is the plane in R3 removing the origin. Okay, the flow is here. Okay, this is the flow of phi. Okay, this is the space R3, and this is the coordinate theta. This flow can be projected using the stereographic projection into the flow. Okay, And then you can use this flow, this stereographic projection, to induce a flow in the sphere as to removing the poles. Okay, this is the flow phi, this is the flow bar phi. Okay, using stereographic projection, you can make a topological conjugation between the flow. This is expansive, but this is not expansive. Okay, this is very simple because 2 points, you can pick a 2 point very close here, and the orbit will be together all the time. This broke okay, they will be together all the time, but they will not be the orbit are disjoint, which is not the property required for expansivity. So this example, then how can redefine expansivity to make it topological conjugacy invariant. This question, okay, I should mention Professor Lee here, which is the young advisor, who can I say is the first person making this kind of question, okay? One situation, one definition appeared in the literature. This is Jung, Nguyen, and Yang, Okay, they introduced the definition of rescaling expansivity. They introduced the concept of rescaling expansivity. Okay, this is an DCDS, I think 2020. Okay, to introduce this definition, to remind you, this definition will use this kind of functional space, which is the set of continuous map, so infinity, such that the pre-image of zero is precisely the singularities of the flow. Okay. Now, what the situation appears here is this. Then those authors defined that phi is topological expansive. I'm sorry, rescaling expansive. Expansive. If for every epsilon number positive, there is delta. Now, this is a function in this functional space. Such that if x and y satisfies the distance between phi t of x, phi alpha t of y, less than alpha, I'm sorry, this is not alpha, this is delta, phi t of x for every t in R, and some continuous alpha from R to R, fixing zero, then y belongs to the piece of orbit of x. Okay. Then those authors proved the following, that this is topologically conjugacy invariant. This is those authors proved this property. However, rescaling expansivity is not equal to expansivity in the compact case. Why? Okay, the example is the Lorentz attractor. Okay. the Lorentz attractor, which are depicted here very succinctly. Okay, the Lorentz attractor have a singularity which is not isolated, and therefore this attractor is not expansive. However, it is expansive. It is scaling expansive. And this was proved by Wen and Wen. This is transaction. 2018 maybe, where they defined the scaling expansivity differentiable version. Okay, I will not. What happened? The differentiable version. I will not define here, but you have to say, you have to see is that the differentiable version implies the topological version started here. And then this is an example of a flow on a compact metric space, which is scaling expansive but not expansive. Now, okay. Inu Yang proposed the following definition as follows. We say phi is topologically expansive if for every number epsilon positive there is a function C plus here, or I have to mention what is C plus X. This is the set of, the deltas from X to 0 infinity continuous. This is different. Look at this. Have nothing to do with this space. Okay, totally different. But here the preimage of delta is the singularities. Here, the zero don't have preimage. Okay. So, okay, let me continue. Phi is topologically expansive if for every epsilon there is a function delta such that if x and y in the space satisfies distance between phi t of x, phi alpha t of y, less than delta phi t of x for every t in R, and so on, alpha continuous, fixing 0, then y belong to the same orbit of x. Okay. As you can see, expansive implies topological expansive. Why? Because, by the way, the name topological expansive, this name appears because precisely to do not confound expansivity and this new definition, and this name is copy-pasted from a paper from Cosillas, a published paper in arXiv. I will not say precisely, but this is, I think, it's 2018 paper in arXiv. Then we took that name from topological expansivity because we found this very appropriate to this situation to differentiate both definitions, the Young definition from Bowen-Walter definition, which are different. Okay. So let me. Okay. So we have this implication: expansive implies topological expansivity. The converse is false. There is a stupid counterexample. You pick up the phi, the trivial flow, which means every point is a singularity. In this case, phi is expansive if and only if the space X is uniformly discrete. While the phi is topologically expansive if and only if the space X is discrete. Of course, uniformly discrete implies discrete, but it's easy to find a discrete space which is not uniformly discrete. You can simply consider this space. In R, you can pick a sequence which will accumulate, but going to infinity in this way. But this is discrete, but not uniformly discrete, which requires a uniform radius of separation between the points. So you can easily find that a flow, a trivial flow, which is topologically expansive but not expansive. Okay, I will give the second example later, a more interesting example, but for the moment, let me state the theorem one. We say that topological expansivity is invariant by topological conjugacy, and also reduce to expansivity in compact spaces. Okay, this is the theorem one, which make a difference with the previous rescaling expansive definition. Okay. Now, an example, a second example here. A second example here is the translation flow. Phi t of x equal x plus t by b multiplied by db, where this is in Banach space, where b is a velocity vector of course non-zero. Okay, what happened with this flow? This flow is phi is topologically expansive, but not expansive if the dimension of the space is bigger than 1. Okay, let me try to explain why this proof. This example is inspired by an example of cosillas, no? Okay, very influenced by this example. Even the proof. Okay, first, we show that phi is topologically expansive. Okay, for that, maybe I have to use a different letter here, but okay. For that, given x1 positive, we choose delta from x to 0 infinity. This delta x is defined in this way: 1/2 norm of the vector b multiplied by epsilon multiplied by 8 minus norm of x. This is for every x in x. Okay, we have then what property have? What is the property of this function? Delta x is less than norm of b multiplied by epsilon, and also delta of x go to 0 as the norm go to infinity. Okay, now let x and y in x such that the norm of phi t of x minus phi s of t of y less than delta phi t of x. This is for every t in R and some continuous s from R to R fixing 0. Okay, suppose that situation occurs. We'll keep a name for this inequality. Okay. Clearly, we can see it clearly. The flow is the time t flow is an isometry. Okay, so this and then because of this we get this phi st minus t of y is less than delta phi t of x. This is for every t. Okay. Thus, st minus t of b should go to x minus y as t go to plus or minus infinity. You get this from the definition of the flow. But as t minus t of b, this belongs to the subspace generated by b, which is and this subspace is closed. This is closed to the subspace. And you conclude that x minus y belongs to the space generated by B. And from this, we get that y is equal phi alpha x for some alpha. Okay? We estimate alpha. To estimate alpha, we just replace t equals 0 in one, the inequality 1, to get the norm x minus y is less than delta x, which by definition is less than norm of p x0. Then norm of x minus x plus alpha v less than norm of b multiplied by epsilon. So alpha, modulus of alpha is less than epsilon. And so y belongs to phi minus epsilon of x, proving that the flow phi is topologically expansive. Now, phi, what happens if dimension of the space is bigger than 1? Well, okay, wait a minute. Okay, sorry. What happens in dimension bigger than 1? The flow phi is isometry by isometries, or flow by isometries. And therefore, not expansive. Here, I think dimension bigger than 1 is not necessary here anyway. Okay. Now, this finished the proof of the example. Another example is that the vector field, which I will not prove here, which is you can use this example. The vector field Vxy equal 1y of R2 is topologically expansive. This example implies this, because what the flow generated by the vector field will be a translation. Okay, that's why it appeared topological expansivity because of the previous example. And now I will state the second theorem, which characterizes topologically expansive flow in terms of Scaling expansivity. Okay, let me go to a different page. Then theorem 2, phi is topologically expansive if and only if phi is Scaling expansive and the singularities are isolated points of the space. Okay, this means that, as you can see in the Lorentz attractor, what happened? The singularity is Scaling expansive, but there is a non-isolated singularity. This implies, of course, not topologically expansive. The picture for topologically expansive flow is some part here, which is there are singularities separated from the space, and this part is this is the picture. If this is Scaling expansive, then the flow is topologically expansive. It's a Scaling expansive flow with several singularities. I mean, with perhaps infinitely many singularities, but all of those separated from the rest of the space. Okay, let me talk about the growth rate of periodic orbit. What is a periodic orbit or periodic point? what is this? There is a minimal T positive colored period such that flow T in P is equal to P. This means this, the orbit is a circle. Okay? And of course, the orbit, the another members of the orbit are also periodic with the same period of P. Now, we use this notation. Vt is the number of periodic point orbit of period less than or equal T. This is given T positive or even positive. Yeah. Singularities may be periodic orbits of period 0, but I will not use this. Now, Bowen-Walter proved the following inequality. That the limb sup, the limb sup of the 1 over T log of the Vt does not grow more than the topological entropy. Okay, where A phi T is the topological entropy, which is the entropy, topological entropy for continuous map of the time one map. Okay, but there is another way to define this A phi, which is precisely by the Bowen-Dinabour formula. Which is lim epsilon go to 0, lim sup T go to infinity, 1 over T log S of T epsilon, where S of T epsilon is the maximal cardinality of what? T epsilon separated set A, which means the following. For all different points in A, there is a time such that the distance between the corresponding iterate at time S is bigger than equal than x. Okay. Now we want to know what if this is okay. The Bowen-Walter inequality was proved for flow phi in expansive flows. Expansive in compact X. Okay, this is the scenario of this inequality. Now the problem is, what if phi is topologically expansive only? This is the question here. And to attack this question, I will introduce an entropy-like number. We are going to define this number. A star phi will be this supremum over the compact of what? Of a star phi k, where a star phi k is equal to the supremum over the function, the positive function, sorry, of lim sup T go to infinity 1 over T log of S T delta K over beta T delta K. Let me define those numbers. Here, S T delta K is what? Maximal cardinality of T delta K separating set A, which is, what does it mean this? For all these different X and Y in A, there is time such that distance between phi S of T X, phi S of Y is bigger than equal delta phi S of X. Remember, delta is a function here, not a number. okay? And this beta is the same as before. Beta T delta K is precisely the infimum of what? Delta phi S of theta, such that theta S belongs to K product 0T. This is a correction number, okay? And to justify the name, we justify that A star is entropy-like, is an entropy by the following theorem. Theorem 3. First, A star is invariant by topological conjugacy. The second is that A star equal A if the space is compact. The third is that if we reparameterize the flow in this way for some A positive, then the entropy of bar phi is precisely the A multiplied the entropy. It starts over here. Here is A star. A star is equal A star of the phi, the original flow. And 4, and we have a Bowen-Dinabout formula. Like formula, which is given by this A star of the flow phi is equal to primum K over the compact subprimum over the deltas positive function in X ln sub T go to infinity of 1 over T log of R T delta K over beta T delta K, where here R T delta K is what? The minimal cardinality of a T delta K spanning set F. And what does it mean? This means that for every Y in K, there is an X in F, such that distance between phi S of X, phi X of Y is less than or equal delta phi S of X is for every 0, S, and T. Okay. So this theorem says that this is the justification for the name entropy for this A star. I mean, the behavior is as good as the classical entropy. And now, to state the last theorem, we use the following definition, which is very natural. Dynamical, we say phi is dynamically isolated at infinity if there is a compact intersecting all regular points, regular orbit of phi. In formula we put in this way: phi t of the x removing k is contained in the singularities of the flow. Okay, that is this property. For instance, F is compact, then every flow is dynamically isolated at infinity. So in the case of a compact metric space, you don't need to this hypothesis is necessary. Okay, you can easily find examples where this property is not true. Okay, not difficult to find. Now, with this definition, we get the following theorem. Theorem 4: if phi is topologically expansive dynamically isolated at infinity, then we get this growth rate of the periodic orbit. 1 over t log dt. The growth rate of the periodic orbit is controlled by A star of the flow. Okay. Of course, this theorem 4 reduce to Bowen-Walton inequality. In the case X is compact. Okay, this finished the introduction of our paper. The details can appear, maybe appears in another, but details, you can see our forthcoming arXiv paper. Okay, you can see in our, when we post the paper, soon we are going to post the paper very soon. Thank you very much.